Hey guys, hope you're all doing good and welcome to a new video. So this time we are just going to be continuing from where we left off. Now, a couple of corrections. I accidentally told that this is a screw type supercharger. It's actually what you call as a roots type supercharger. So the idea is that along this taper, the air is going to get compressed as the screws rotate, because it's a positive displacement machine. The air is going to be moved, and since the available volume for the air is getting reduced, it's going to get pressurized. On the other hand, on the roots blower type, you don't have any taper. You can see that here quite clearly. So the idea is the air basically gets sucked in from the top, and what's going to happen is as the lobes rotate, it's just going to get pushed sideways, and that air is going to get stacked towards the bottom, thereby pressurizing it. Alright, so what we're going to do now is we're just going to flag the inlets and outlets. So I'm going to basically select the angle method, select this guy and assign it to a new boundary. And then we're going to be selecting this guy and we're going to be calling this as the outlets. Now, these two parts are going to go back to the casing itself. So I'm just going to click on apply. Alright, now we don't want our outlet to be like too close. In reality, this supercharger unit is going to be sitting on some type of an intercooler, right? Because compressed air is hot, right? And you want to cool this hot air before it enters the engine. And since we actually don't have that geometry, what I'm going to do is I'm going to manually push the outflow boundary a little bit farther away, right? Is this correct? Well, it's not, but it's not a big deal, because say that you are actually working on a realistic supercharger, then you have the outlet at the right portion, so you don't have to make any guesses. So in my case, what I'm going to do is I'm just going to translate selected boundary, and I'm going to select this guy, and we are going to be translating this along the minus y direction. Alright, so let's start by moving this by 5 mm to see if it looks right. 10, 15, 20, 25, 30, 35, 40. Alright, so that's, I think, a good starting point. Again, this portion of the geometry is usually available if you are working for a OEM or if you are consulting for a OEM, right? So this shape is not super realistic. That's not a big deal because the shape does not matter in our case. All right, so I think that looks good. So the next thing that I want to do is, you can see that the origin is kind of out there, right? So what I want to do is I want to center the origin maybe on this particular point. So what I'm going to do is I'm just going to measure location. I'm going to select this particular vertex, click apply, and I'm just going to take this point, right? So this is basically the location of this point with respect to this particular origin, right? So I'm going to transform, but this time I'm going to use something called as the delta method. I'm just going to put the copied coordinates here. Now what I want to do is I want to translate my geometry. This point is basically 0.0737 meters away from the x-axis, right? So if I push this point by this distance in the negative x direction, then I should basically move this towards the left, correct? So if I put a negative sign here, it's going to make sure that the x coordinate of that red point is 0. So if I basically do the same thing for all of them, then essentially what I'm doing is I'm moving this red point to the origin, right? So let's make sure that entire surface is selected, and let's click on apply. There you go. So now you can see that the entire geometry has been shifted. Why did I do that? Well, this actually helps me provide the rotating boundary conditions very easily. Now for this particular lobe, we know that the rotation axis is z-axis and the rotation center is 0, 0, 0. And if I measure this guy, ideally you will see that you just have an offset along the x-axis, right? You can see that along the x-axis there's an offset, that is the lobe to lobe distance, and pretty much the y and z components are like 0, right? This is a very small number. So this helps us in assigning our boundary conditions with ease. So what's next? Well, the next thing is to basically assign the boundary conditions for our lobes and apply the pressure conditions for the inlets and outlets. So where do these data come from? Well, you usually get them from something called as a performance curve. Now, typically for a supercharger, when it's rotating at a particular RPM, it basically delivers a given mass flow rate for a given pressure ratio, right? So the idea is that depending upon the RPM and depending upon the mass flow rate and the pressure, you have a particular efficiency for the supercharger. And the idea is to basically have all these details when you're starting to simulate. Now, as far as the CFD engineer or the CFD analyst is concerned, The only thing that you need to be worried about is choosing a point that is still inside this performance map. Oftentimes you might be playing with a supercharger case setup and you might be using a boundary condition, you might be using an operating point that is completely not realistic. In those cases you will definitely get wrong results. So from a CFD analyst point of view, you need to make sure that you get your hands on this performance data so that you can definitely be sure that you are setting up the simulation for the right conditions. So in our case, what we are going to do is we are going to go for a pressure ratio of 2.0, which means the outlet to inlet pressure is going to be 2.0. which means the ratio of the outlet to the inlet pressure is going to be 2.0. So at the inlet, if the pressure is 1 bar, the pressure is going to be 2 bar at the outlet. And in our case, we are going to say that the rotor is basically rotating at 36,000 RPM, right? So 36,000 RPM is nothing but 36,000 divided by 60 RPS, rotations per second, right? Since 1 minute is 60 seconds, you're dividing this by 60. And then what you're doing is you're converting this rotations per second into degrees per second. Now one rotation is 360 degrees. So you take your original RPM, you multiply that by 360 and divide that by 60, right? Now 360 by 60 is equal to 6. So the only thing that you're left with is 36,000 times 6, which is 216,000. So this is going to be the speed at which the lobes are rotating. Alright, so the next thing that you need to understand is the direction of rotation, right? So we definitely know that the lobes should be rotating in opposite directions, correct? But you still have two ways to do that. So the idea is once the air comes in, we want to push it towards the outer wall and then we basically bring it towards the outlet from the downside, right? So in other words, if I hide this guy, this orange rotor should be rotating in clockwise and the yellow rotor should be rotating in anti-clockwise direction. Alright, so that's basically it. So let's go ahead and set up the case. So I'm going to start with begin case setup. I'm going to click on general flow, click on apply and done. And then in this case, I'm just going to have air as my material.